get a verbal warning sometimes, but not this time. Okay, so for this sort of first lecture, I said it's going to be informal. I've done some significant preparation, but not as much as I'd like to do to polish it properly. But I am writing lecture notes and in very crude form, and I'll make them available online. The other rule for this thing is jump in. If you've got a comment or question, or you just don't understand something, then I'll try and answer it, or Joseph will jump in and answer it. But anyway, the whole idea is just to sort of talk about the subject. I'm going to, for the first lecture, try to give you the bigger picture. Admittedly, it's going to be sort of in the details of the supergravity, but I'm not going to dive into the solving of differential equations until probably the next lecture, and in particular setting up the BPS equations. I want to spend the first lecture sort of exploring the bigger picture of where it sits in supergravity and in 2B supergravity, and then and talk about some of the ideas that go into making supersymmetric configurations. And I have somewhere here just to share screen. I actually started I made some slides of this, so to start the whole thing. Interesting. Okay, it seems to be operating good. So basically, interesting. Maybe I should do this by going to full screen rather than sharing a screen. Well, this is probably smarter. Let's see view full screen. Can you see all of that? Can everybody see things or not? Everybody's mute. I can't hear a bloody word anybody's saying.
It's fine for me.
Good.
Yeah,
Okay.
if you mouse, you can see stuff.
Good. Okay. So basically, I want to close out this window. I don't want the, well, much as I like you, I don't want to see you while I'm doing this. Okay. So basically, this is sort of going to be all about the actual underpinnings about how Joseph and I and the whole gang, Stefano, Rodolfo, Masaki, Emil, myself, and David, we started evolving these techniques for building these microstate geometries. And I gave some lectures last year, which is, in a sense, going in an orthogonal direction, but making microstate geometries, but in a rather different way. And I'll remark upon that when we go. But those lecture notes are already online. They went up on Christmas time, December of last year. Anyway, so we're going to talk about making superstrata. Oops, now it won't advance. This is annoying. Oh, there we go. Okay. So basically, the definition of things is they're basically smooth horizonless solitonic solutions to the bosonic sector of supergravity, the Lorentz limit of string theory, with the same asymptotics as a given black hole or black ring. That's a microstate geometry. And in particular, we're going to talk a lot today about the particular bosonic sector of a particular supergravity that we're interested in to make superstrata. So that's really part of the major purpose today, is to isolate that theory, figure out the degrees of freedom, and talk about the supersymmetries and all that sort of stuff, and then get down to the BPS equations next time. So essentially what we're going to try and do is take a standard black hole configuration and resolve the singularity and remove the horizons. And the whole point of this is, of course, you want to avoid the information problem, but still have something that looks and behaves just like a black hole. And the whole goal of these lectures is to construct the microstate geometries, but particularly aimed at getting at the superstrata story. Okay, so basically, I'm going to say very little about the CFT, but of course, I need to kind of motivate why we're doing the particular construction we're doing. So underlying this whole thing for superstrata is we work in the D1, D5 frame, duality frame in 2B supergravity. So that means that basically the D5s and D1s are what D1s live inside the D5, and we wrap the D5s on a T4, and then there's a common S1 which will always be called Y, or a null coordinate V, common between the D1 and D5. And we're going to talk a lot about the supersymmetries that you have in certain Brane configurations. But particularly what you should sort of take away immediately is we're looking at going to be looking at things that are starting out to be quarter BPS. And this is the sort of starting point of Samir's sort of original program on fuzzballs, where he looked at the smooth geometries you can get from the D1, D5 system and the Supertube. And we will go through that in great detail later. And we're always going to compactify the Y direction on some circle. Okay. So now, transverse to this, there is a spatial four manifold, and we're going to have a lot to say about the geometry of that spatial four manifold, but in the Brane configuration, everything is just flat for the moment, and we're going to leave it as flat. But superstrata, so what are they? They are the microstate geometries that you get by taking the original D1, D5 system, turning it into a supertube, or making it smooth by turning it into a supertube, and then adding some momentum waves, a coherent collection that are visible in supergravity of momentum waves. And you pick left movers or right movers, it doesn't matter, but you can only have one direction of motion, because the momentum chart, to have a BPS solution, you have to have a purely left moving or purely right moving momentum charge. And we're going to talk all about that too. And so they are 1/8 BPS, where the momentum, adding the momentum, breaks half the supersymmetries again. And it's supersymmetric because, in this language of the CFT, the right moving sector is still in its ground state, and therefore supersymmetric. So the goal of these lectures is really going to be aimed at building precisely the fully supergravity backcorrected version of these in a way that makes a smooth microstate geometry. If you simply do what I've described, you simply put in 3 charges and you don't do anything interesting with it, you wind up with just the 3-charge black hole, the D1, D5P black hole. So part of what we're going to be talking about is how you avoid the inevitable formation of a black hole, and how you turn this configuration into something that is smooth and actually makes holographic sense. So that's sort of where we're headed. But what I want to do is sort of put this into the context of broader supergravity, and talk about where this comes from in terms of the compactifications and what the degrees of freedom are and why certain choices are made. And that's really where I want to sort of survey the supergravity picture. So I've got some annoying feature on my screen. Okay, oh, never mind. So basically, the starting point before you go any further is to just simply do the most trivial thing. You take the T4 compactification of 2B supergravity. We'll talk about K3 in a few minutes. But if you just do the thing that Kremer and Julia did 40 years ago, I guess, but down to 6 dimensions. See, well, basically, I should remind you that we're looking at this we want to look at the T4 transverse to the Brane. So the first thing we're going to do is deal with this trivial piece of space-time and wrap it up and get rid of it. So basically, we're going to look at the T4 compactification of 2B supergravity. You can also think of it, and if you're just for getting the degrees of freedom right initially, you can also think of it as the T5 compactification of M3, and you just teed your eyes on a circle. But I want to just identify the degrees of freedom. Okay, so when you do this obvious descent, you get I'm looking from the point of view of M theory, if you get a metric in 6 dimensions, you get 5 Kaluza-Klein fields because you get vector fields, and 15 scalars, which are the shapes of this T5. In 2B, these come about in a different way, but the 6-dimensional degrees of freedom are still the same. The 3 form in M theory gives you 10 scalars from 5 times 4 times 3 choices here and so forth, another 10 vectors from here, and also, most importantly, when you put one internal index and two space-time indices here, you get 5 rank 2 tensor gauge fields, and the tensor gauge fields are going to be a huge part of this story. And the last part of this beast here is this becomes in 6 dimensions a 3 form, which has a 4 form field strength, which you dualize to a Maxwell field, so you get one more vector field. And for the heavy lifting that was painful that I did in the last day or so to get this lecture sorted, I've never gone through the details of how the fermions work, but it's actually very useful and instructive to do. So you start with an 11-dimensional supergravity, and you reduce down to on a T4, and then you find that there are space-time gravitini which carry this index alpha. This alpha is actually an SO5 spinor index or USP4 index, and there are 4 of each of them. Now, I'm going to dive into this business about the fact that sometimes in the literature this is called 4-4 supergravity. I'll get back to that later, but it's because there are 4 gravitini with one USP4 and 4 gravitini under another USP4. And then the internal guys give you a non-chiral 20. Basically, there are 5 values here and 4 values here, and then the opposite helicity over here of these spin half fields. So basically, when you get down to the bottom, the field content in 6 dimensions is a graviton, 16 vector fields, 15 here and 1 from here, 5 tensor gauge fields, it sounds like, what was it, the 12 days of Christmas, 25 scalar fields, 4 plus 4 gravitini, and 40 spin fermions split evenly. The plus and plus means left and right-handed helicity in the obvious sense. So if you just do that naive thing and just start with 2B supergravity, you go down to 6 dimensions, you'll start with M theory, that's what the content of what you wind up with. And you have basically 32 supersymmetries. Oh, I forgot to say, there's a bosonic coset. The model, there are 25 scalars, but you should think of it as essentially this is the usual symmetry you would get on a T5 compactification of M theory. It becomes an SO5-5 symmetry, and the coset is SO5 over SO5 times SO5, and that's how you parameterize the 25 scalars. But there is this global symmetry coming from the compactification. Indeed, another important aspect of this discussion is going to be that you should think of the tensor gauge fields not as being 5 tensor gauge fields, but you should, in 6 dimensions, it's really important to break them into, use the duality to break them into the anti-self-dual and the self-dual tensor gauge fields. So there are indeed 5 tensor gauge fields, but break them into self-dual and anti-self-dual parts in 6 dimensions. And then this forms a vector of 10 objects, which do indeed transform under that global symmetry. And also, the global symmetry acts on the fermi, on the spin half particles. These are almost irrelevant to what we're going to say. This 16 is the 16 or spinor representation of SO5-5. And the other thing that's also very important that will become apparent later is that the indefiniteness of the signature here has everything to do with the particular quadratic forms that will turn up and so forth throughout the whole thing. And it does also distinguish between the self-dual and the anti-self-dual parts of the tensor gauge fields. So far I've done nothing. All I've done is done a trivial compactification and elucidated the sort of degrees of freedom that turn up. By the way, these pieces of tech are basically I trimmed straight out of the file I was typing up. So this will all, I'll put it online sometime today or tomorrow once I've corrected a couple of mistakes I found. Anyway, so this is the content, straightforward, the straightforward T4 reduction. And then the other important point is the R symmetry really is this SO4 times SO4, but you should think of it as USP4, it's spin representation. And then these spinners all transform under the USP4 on one or USP4 on the other. So that's the sort of content of the 2B theory once you get it down. What our task really is going to be to pare this theory down to the thing we really want to look at, which is going to describe the superstratum. So any questions at this point? Seriously, guys, I'm very happy if you jump in. Everybody's going quiet. Okay, so what we're going to do now is talk a little bit about the supersymmetries in general. So there's this horrible notational ambiguity. I called it 2-2. In half the literature, you'll find it called 4-4. This is an old school thing. The reason why some people call it 4-4 is because there are 4 gravitini that are left-handed and 4 gravitini that are right-handed. So it's sometimes called 4-4, but I'm calling it 2-2. And the reason why is that there's this weird thing that happens in I think it's 5, 6, and 7. I know it's certainly 5 and 6, but I think it's also 7 dimensions. That you have to impose, you can't impose a Majorana condition on the spin on a single spinner alone. You have to do it with a symplectic pair. So you need 2 spinners to make a symplectic Majorana condition. What this really means is you ask yourself the following question. How many real SUSIs, how many real spinner components do you need to make an irreducible spinner representation? And so in 5 and 6 dimensions at least, what happens is that the spinners are intrinsically complex, and they're 4 spinners. But you can't impose a reality condition without relating them to another spinner. So really, when you count the number of independent irreducible spinner representations that are real, that has 8 individual components. And so I call it 2 plus 2, 2. It's called 2, 2 because there's 2 on left-handed, 2 right-handed times 8, which makes 32 supersymmetries. But some people call it 4 and 4 because of this business here. Anyway, this is the old school what's going on in 5 and 6 dimensions is you have 4 component spinners, but then 8 real SUSIs. The old school labeling and counting is therefore can be immensely misleading because the 4-4 or 2-2 is throughout the literature. So every time you pick up a paper, it can drive you nuts, wondering whether they're dealing with something with 16 SUSIs. The almost unambiguous way to do it is, I think, the modern, more rational way, except there's a caveat here, that you just count the total number of real supersymmetries. And so this thing has 32 supersymmetries. It's called 2-2. And so as we go to half BPS and quarter BPS, we start paring this number down and dividing by 2. Okay, so beware of old people doing supergravity. Right, so now we're going to go to 16's half maximal supersymmetry. And we're ultimately going to go to quarter maximal because we're after the D1, D5 system. But I'm going to go in steps because I want to set the supergravity story in place. So first of all, half maximal supersymmetry means 16 supersymmetries, but there are 2 choices, and I may flip this around at some point. The 2 choices are simply, do I lose all one of helicity, or do I lose one of each helicity? And there are 2 classes of theories and everything else. And we have to choose one of these, but there's one we need to choose. So basically, the question is, what's the chirality of the supersymmetry and the R symmetry? And the 2-0 theory has 2 chiral supersymmetries and a USP4 super R symmetry. And the 1-1 theory has SUSIs that are of both chiralities with an SU2 cross SU2 R symmetry. So basically, there are 2 classes of theories, and when you see something called 2-2 in the textbook, it might, or in a paper, it might be actually the 1-1 theory in this notation. This is the really awful part of this old discussion. So this is the theory of 16 supersymmetries, but there are 2 choices, and you do need to distinguish them. So 16 isn't good enough to tell you what theory you're dealing with. You have to tell me whether it's the chiral theory or the non-chiral theory. Okay, so our focus entirely is going to be on, I've now reversed it, the 2-0 theory. And basically what I want to do here is talk about why we do this. First of all, the simplest, crudest way you can think about this is we're going to require the supersymmetry to satisfy some kind of chirality condition. Now, the T4 directions throughout at least this lecture are going to be labeled 6, 7, 8, 9. I want 0 through 5 to be the 6 dimensions by the time we're done. And typically, the way you impose it, you can choose one sign or the other. It doesn't really matter. That's 2-0 versus 0-2. But we impose this projection condition or chirality condition on the supersymmetry. And I'll explain why we do this in a few minutes. But remember in the 2B theory, the spinners are already chiral. They already satisfy a projection condition like this. So that means that since the product of all the gamma matrices, and since you're posing this condition, it means that the first 6 gamma matrices on the epsilon project to epsilon. So what it means is that because of this chirality condition, you start with a 2B supergravity theory. It's chiral. And when you use this projection condition, it descends to what is the 2-0 theory in 6 dimensions. In other words, it's got 2 chiral supersymmetries. It's not the 1-1 theory. So all this to say, we're going to jump on the 2-0 theory because it's precisely the one that keeps the chiral supersymmetries and involves this projection condition. Now, why do I do this? Well, there's one other reason why this is useful and important, but there's a much more fundamental reason to do with the branes. But let me just make the following remark. When you do this kind of compactification, there's another very important compactification, which is the K3 compactification. It produces the same class of 2-0 theories, and I'm going to explain how they differ later in 6 dimensions. But this condition here comes to the Hall-maximal condition. And I think I'm going to break out of my full screen for a second. I don't want to stop sharing. How the hell do I get out of full screen? Escape.
You press the green button.
No, I want to actually. I'm going to do the screen sharing. I want to share new share. There we go. I want to go to another app. Excuse me 1 second. I've got some way of scribbling. Yeah, I think this will work. Hopefully this will work. Yeah. So basically, I just want to make a comment. So we're going to think about the K3. Can people see this?
Yep.
Good. Okay. So basically, I want to think about K3. And if you want to preserve supersymmetry in K3, there's a Hall-maximal condition. You want to solve this equation. Oh dear, horrible. Sorry, I don't have getting used to this pad. You want to solve this condition. And that turns out to be equivalent to an integrability condition, which is that R mu nu AB times gamma AB on the manifold is 0. Now, on K3, this has the property of being self-dual. And so this condition is basically equivalent to saying that if you want to solve this thing, if you have the following property that gamma AB is equal to 1/2 epsilon AB CD, gamma CD, if that is true, oh, sorry, if you impose that condition, sorry, I've written this wrong, incorrectly. Let me write it slightly differently. What I want to say is the following. Sorry, I said it incorrectly. I'll get it right. Gamma AB, that's what I should have said, minus 1/2 epsilon AB CD, gamma CD, acting on epsilon, should be 0. Because the self-dual, if this is self-dual, then this always comes with this. And as a result, this imposes that condition. But if you take any one of them, you get gamma 1, 2 is equal minus gamma 3, 4. I should use my correct notation, 6, 7, gamma 8, 9. Acting on epsilon is equal to 0. At which point you multiply by gamma 6, 7, and I may have got the signs wrong, but basically, morally speaking, this condition is precisely what you need to solve the integrability condition of this equation. So you want a covariant killing spinner on a K3, you have to solve an integrability condition that involves the curvature. The curvature on K3 is self-dual. And if you have this condition, it guarantees you have a solution to this. But this condition is precisely this object. Now, another way to think about this, and we'll talk a little bit more about this later, is think about the tangent space action here. There's a tangent space which is SO4. And what this says, but SO4, remember, is isomorphic to SU2 cross SU2. And what this says is that the spinner solutions decompose into the epsilons are in a doublet singlet plus a singlet doublet. And the Hall-maximal, the presence of this Riemann tensor kills these off. Some of these get broken, but this remains. And so the supersymmetries form a doublet. And this projection condition says, I only want a very particular doublet under the SU2. So that's in some sense the origins from the point of view of K3 of why you have this chirality condition. Essentially, you're interested in making sure you can solve the killing spinner equation on the space in question. But what you then find is that under the obvious tangent space symmetry, the spinners that survive this are in a doublet of one of the two SU2 factors of the Hall-maximal group. So let me go back to sharing my new share. Go back to that. I think that's desktop. No, sketchbook, lost it. I've lost my presentation. Keynote, no. There it is. Right, tools, view, full screen. Okay, so all this to explain that there's a very natural purpose for that helicity or chirality projection condition. If you think about K3 compactifications, it will also put you in exactly the same class of these two zero theories, but this is now mandated by Hall-maximal. On T4, this is a choice, but it's going to be a choice that's extremely natural in terms of the branes. So any questions about this? Seriously, I'm talking in a void here, and normally in a class I get rumbles and shuffles and comments, but please jump in.
Can you not make that choice? So you said that on T4 this is a choice. Are you
Yes.
make that choice?
You don't have to make that choice, you'll be back in the maximal theory. But this choice is going to be also a consequence, as we're going to discuss in a minute, of the Brane configuration I'm ultimately trying to model.
Oh, okay.
Why I'm carrying this along here is I'm just saying we're going to make a choice, but this choice will be motivated because of the branes I've got later. And we're going to, believe me, we're going to dive into the Brane projection conditions in some detail. So it's a choice at the moment on T4. You don't have to make it, but I'm pointing out along the way, this holonomic condition is exactly what you need to get also a 2-0 theory from K3 compactification. And the other important takeaway message is that in 6 dimensions, the theories we've got have chiral spinors. Any other questions or comments? Okay. So what I want to do is take you through the breakdown. We're now going to decompose the maximal theory into the structure of the 2-0 theory. And the beautiful thing about the 2-0 theory is it's really rather simple. So now what happens is you wind up with a theory which has one gravitino, but now you've got half the amount of supersymmetry. Sorry, that should be graviton, excuse me, but one graviton. You have 4 left-handed gravitini. You've lost the right-handed ones. It's the 2-0, not 2-2. And then you've got 5 anti-self-dual tensor fields. So you're basically in the graviton. The self-dual guys wind up in the graviton multiplet. And this is going to be a theme that basically the gravity multiplets will always involve self-dual tensor gauge fields, and the other multiplets, the anti-self-dual tensor gauge fields, wind up in the typical 2-0 tensor multiplets. Now, another word of warning. Some significant portion of the literature have this convention exactly reversed. That there is a correlation between or universal correlation between the handedness of the gravitini and the duality of the tensor gauge field that winds up in the gravity multiplet. But some people have this right-handed and anti-self-dual. I think Henning-Santleben has exactly the opposite of everybody's.
Oh, nice.
So this is part of the reason, why a course is sometimes useful. It's the warning for all these horrible things. Okay, so once you go down to 2-0 theory,
other condition would be absolutely horrible.
Yes, I thank you, Ruben. I completely agree.
Because that would be also implying a convention where on K3 the hyperkähler structure is made of anti-self-dual forms instead of self-dual forms.
Yes, yes.
It's absolutely moron.
A bad after my own heart, indeed.
So but you should outlaw the other convention.
Indeed, I think we can try and do that. But anyway, part of the point, my purpose here is to warn you about some of the bizarre conventions, and we are guilty of some because of which I'll come to probably next time on it. Harvey Rial uses an extremely strange notion of Hodge duality, which can drive you nuts. Anyway, I'm trying to warn you about where as we say in England, the poo traps for heffalumps are. Okay. So in particular, the other part of this thing is there are 2-0 tensor multiplets, and they have a tensor gauge field, and then the handedness of the spinors is the opposite of this handedness, and then there are 5 scalars in this multiplet. There are no 2-0 vector multiplets. Those vector multiplets only occur in the sort of 1-1 version of the theory. So that's what makes the structure of this theory relatively simple. Now, again, what's happened here is that the 4 in breaking the sort of left-handed supersymmetry or the other handedness, right-handed supersymmetry, again, there's a typo. I take it back. Breaking that, I've got it the wrong way around. Okay, what I should have said here is that essentially you've gone from 2-2 to 2-0, and a bunch of gravitini have become massive. And this statement is correct. The 4 right-handed gravitini have become massive. But what's happened is that basically all the left-handed spin-half fields have gone with it, and all the vector fields have gone with it as part of this sort of super Higgs mechanism. So the making massive of 4 right-handed gravitini have destroyed all your vector fields and taken them away. So basically, the massless content is now reduced down to the 2-0 gravity multiplet. But the interesting thing is that, remember we had 5 self-dual and 5 anti-self-dual guys. What now happens is that you still keep, how to put this? The gravity multiplet contains 5 self-dual tensor gauge fields. In the 2-2 theory, you still had 5 anti-self-dual tensor gauge fields. They have not become massive. They are still there. The things that have become massive are the vector fields that were in the original theory and all the left-handed spin-half fields. So the other 5 anti-self-dual tensor fields are still in the theory if you just do this truncation, and they turn out therefore as 5 anti-self-dual tensor multiplets. So this theory that you get from descending the 2-2 theory down to 6 dimensions actually is 2 0 supergravity plus 5 2 0 anti-self-dual tensor multiplets. And there is still the same SO5-5 symmetry, and there is still the 25 scalar fields, and they still sit in this coset. So basically, the 2-2 theory, if you just get rid of the supersymmetry by breaking it, if you put on K3 you get more tensor multiplets. But if you go from, if you just go on the T4 and remove everything you need to break that supersymmetry, it takes with it all the vector fields and the spin half fields that are left-handed, and leaves you essentially with 2 0 supergravity plus 5 anti-self-dual multiplets.
Quick,
Yeah, go ahead. Yep.
On K3, do we get rid of the vector multiplets as well?
Yes, I think they're all gone in this language, but somebody jump in and correct me if I'm wrong, because what generally happens here, as I was just saying at the bottom, is that the generic 2 0 theory that's going to be of interest is going to be 2 0 supergravity coupled to n tensor multiplets, and then the coset goes in the obvious way, and the SO5n acts in the obvious way on self-dual and anti-self-dual. And I think, if I counted right last night, the K3 compactification gives you 21 tensor multiplets. Is that right, Ruben? Do you know?
That's right.
Good. Okay, I did count it correctly. Where do they come from? K3 has a signature. If you look at the two forms on K3, how does it come about? The two forms of K3 come with a 19,3 signature, 19 anti-self-dual, I forget the right way around, and 3 self-dual.
Depends on convention.
Yeah, and so basically
it's 19 anti-self-dual, 3 self-dual, then you have 2 B fields, each
yes,
of which has 1 self-dual and 1 anti-self-dual.
Exactly. So the important takeaway thing is it's 19,3, and therefore there are exactly 16 more anti-self-dual guys than there are self-dual guys. So when you add 16 more to this, this SO5 becomes SO21. That was the way I counted it last night anyway. So the point is that the theory of interest we're going to be interested in is going to be some version of this theory. If you do K3, you get n is 21. We're going to be very modest. We're only going to consider the cases for superstrata you only need at most n is 2. You can go further if you like, but we're going to think really mainly about n is equal to 0, 1, and 2. Okay, so we're going to go one more step. We want to break it down to this supergravity. The reason why is basically because the motivation at the beginning, we're going to think about the D1, D5 system. That means a quarter BPS. So we're going to reduce the supersymmetry by a factor of 4. So 2, 2 will first go to 2, 0, and then it goes to 1, 0. But it means the theory we really want has got 8 supersymmetries. And the massless multiplets are, again, somewhat complicated, but I'm just going to I want to show you where the bodies are buried. So once again, there's a graviton multiplet, some left-handed gravitinos, and now still once again, the theme runs on that the self-dual guys wind in the gravity multiplet, and that the self-dual guys in the gravity multiplets. There's some gravitino multiplets we're going to talk about in a minute. And then once again, there's a tensor multiplet, but it's sort of it's been paired back. It's anti-self-dual still. There are 2 right-handed spinners and 1 scalar. There are also vector multiplets, and there's also hypermultiplets. The hypermultiplets do what they usually do, but there are 2 kinds of gravitino multiplets. Now, this is slightly evil. These are massless gravitino multiplets, and if they're massless, they don't make sense without having the extra supersymmetries, so we have to super Higgs them when we get rid of them. But the one that we're going to basically deal with the most is this one, and this one is the one that's going to disappear. So let me sort of explain what I mean. In terms of these 1, 0 multiplets, the 2, 0 graviton multiplet is really rather simple. It's 2, 0 multiplet is really simple. It's simply this and this, because remember the original 2, 0 multiplet was 1 graviton, 4 gravitini, and 5 self-dual tensor gauge fields. And similarly, the original tensor, the 2, 0 tensor multiplet is 1 tensor multiplet, which has got 1 tensor field, 4 spinners, and 5 scalars. So basically, it's a really simple combination to get to 2, 0. But if you want to look at the original guy, this is its decomposition. It's a whole bunch of gravitinos and graviton multiplets, but the real thing is this. What we've done is these G2 multiplets and all the vector multiplets have all been made massive. And then what we're left with is this combination here, which is the 2 zero graviton multiplet, and then the 5 tensor multiplets. So that's really the sort of evolution of these ideas going from 2, 2 to 2, 0 to 1, 0. And it's really the 1, 0 theory we want. And it's really this content that we want. So this is the sort of supergravity setting, and we're just going to be truncating away fields, but I now need to sort of begin to explain why. So bottom line, the theory of interest that we're going to deal with is a theory with 8 supersymmetries. It's going to have n tensor multiplets, and as I said, n is going to be 0, 1, or 2 only. You can add more, but n 0, 1, or 2. It's got a graviton, 2 left-handed gravitinos, 1 self-dual tensor gauge field in the graviton multiplet, and then the anti-self-dual fields. There are going to be n of them in general, and they're going to be n scalars, and it involves, there's a bosonic symmetry, which is SO1n. Remember, the self-dual and anti-self-dual Gauss transform as a vector under this. And there's a scalar coset. S is S0, 1, n. And the important examples for us are going to be n is 0, 1, or 2. So that's the sort of supergravity setting, that how it descends out of the 2B theory. And when I've finally solved the BPS equations, I'll show you how to reassemble the 2B theory out of the solutions I get. But I want to now sort of get to the heart of why this is the particular set of theories we're going to talk about. So now we go back to the Brane configuration. So before I go here, any questions? Let me pause, see if there's any issues, concerns, and so forth. So that was a sort of orgy of supergravity, and we're going to try and now motivate that by talking about the supersymmetry of the Brane configuration, why I go there. Any questions or comments? Okay. So even though you don't have to do the Brane, do microstate geometries in this configuration, the whole motivation for what I'm doing is entirely driven by this supergravity configuration I want to consider, the dual of this. And so the question obviously is, what are the supersymmetries in this configuration? And whoops, basically I want to remind you, and you can find this in a whole bunch of places, that the minute you start throwing down branes, it requires you to project or reduce the supersymmetries. And there's a standard formulation for doing this in string theory, and I can give you plenty of references. There'll be references to the notes, but whatever supersymmetry you've got has to satisfy some kind of projection condition. So there's going to be a projector on Q, and then the projection is set by a bunch of gamma matrices. And in particular, essentially, you can put a plus or minus sign here. That depends on whether you take positive or negatively charged Brane configurations, but there's an arbitrary sign choice here. But once you've set it, you're stuck. And then what happens is that you get a different projector for each and every different kind of Brane configuration. And so at the outset, we're interested in that guy. We're interested in D1s and D5s. And these are the directions on which, unfortunately, I copied this from a paper where this should be 0, 5, and this should be 0, 5, 6, 7, 8, 9. We'll get to that in a minute. These are the directions in which the Brane wraps. Now, what the sigma matrices are doing in all this stuff is you've got to remember you're dealing with an n equals 2 theory in 10 dimensions. And so there's got to be some projection, or possibly a projection matrix that involves the internal internal spinor label in 10 dimensions. So we're interested in these projectors, and this is the directions on which the branes wrap. And this is something that acts on the internal thing. Later, we're going to be interested in the Kaluza-Klein guy. And in particular, we're also going to be interested in the momentum guy. And also, subsequently, we're going to be interested in looking at the fundamental string and the NS5 brane. But for the moment, we're going to concentrate on the yellow ones, the ones that deal with the D1 and D5 system. So we need to correctly label the wrapping direction. So this is going to be my convention. Basically, throughout this, the space-time I'm ultimately going to wind up with is 0 through 5. And there's a transverse spatial M4, which is going to play a huge role in the discussion. The coordinate here is going to be labeled Y, T is the obvious thing, and then the T4 is going to be 6, 7, 8, 9. And so for this configuration, the projection conditions on the supersymmetries are pi d1, which basically is along the 0, 5 direction, or ty, and then this is along the 0, 5, which is ty, and the t4 direction, 6, 7, 8, 9. So those projectors have to be imposed on the supersymmetry, but the thing to notice is that they also, if you have this condition, they also imply, because if you put in the fact that gamma 0, 5, sigma 1 is -1, you put it in there, you find exactly this condition. So this is the fundamental reason why, if in the Superstrata story, we are interested in this T4 projection condition. Once, if you're looking for the supersymmetries in the presence of these Brane sources, you have to impose these two conditions, and those two conditions imply this helicity projection on the 4 torus. So that should answer that question. It's also K3 and Hall-maximal, but that's another reason. So the motivation for this first projector is precisely that. But there's a second projector. We have to do 2 projections, and any 2 out of these 3 conditions will produce the third. So the projector is what gets us to the 2-0 theory. We now need to sort of talk about how you get to the 1-0 theory. And so that involves adding pi d1 or pi d4. As I say, there are 3 projectors, but only 2 of them are independent. So that's the first step. 2-0 theory, and then adding this further projection gets down to 1-0. Okay, now laying down a little bit for the 1-0 theory, when we're done, is going to be the supergravity plus these tensor multiplets with 8 supersymmetries. So the starting point is going to be the theory, which is in the background of 2-charge background, which is basically the D1, D5 system. And within that theory, we're going to look for what would be called half BPS states of this quarter supersymmetric theory. So you start with something with 8 supersymmetries, you look for half BPS, it's got 4 supersymmetries, but you should think of that as being 1/8 BPS states in 2B. So the calculation we want to do for superstratum is we want to set up the 1-0 supergravity in 6 dimensions with a certain number of tensor multiplets. That theory has 8 supersymmetries, and then we want to look for the configurations in that background that actually carry a momentum charge. And that means one last projector on the supersymmetry. Okay, so that's the sort of background setup. We're going to build the 1-0. We're going to look at this particular supergravity theory. We're going to look at these tensor multiplets, and we're going to look at this one, and we're going to look for configurations in that theory that satisfy this projection condition. And there's another thing that's also sort of so much part of the woodwork in this story that it usually gets sort of left out. But when you start throwing together projections, you've got to ask the question, are they compatible? So what that really means is, do these projectors commute with each other? And the answer is absolutely yes, because these signal matrices are the same, and gamma 0, 5 commutes with gamma 0, 6, 7, 8, 9. Are these compatible? Yes, this commutes with this. If they're incompatible, you calculate the commutator, and that gives you another projection condition. So it's possible that if you start using incompatible projectors, ones that don't commute with each other, you've broken the supersymmetry much further than you thought you had. But the rule that a projector cuts supersymmetry in half is true so long as, if you compound the supersymmetry, so long as the projectors commute with each other. If they don't commute, you may have completely broken all the supersymmetry. So that's usually expressed in terms of compatibility. And the beautiful thing about these projectors is that they're as compatible as you could want. So therefore, this is what makes it 1/8 BPS in 2B.
So a quick question.
Sure, please.
What happens in the 1,1 theory? Like the projectors don't.
Oh, that's a good question. I haven't looked at the 1,1 theory. I don't know what it does. The 1,1 theory, though, there is another route probably to the 1-0 theory that goes to the 1,1 theory. Does anybody know this? It's probably more naturally written in terms of M theory because it's non-chiral. In fact, the 1,1 theory is probably most easily described in terms of taking a T5, compactifying down to 6 dimensions and throwing out a different half of the supersymmetries. Short answer is I don't know. The 1,1 theory will contain vector multiplets. In fact, there are papers, I was trying to remember where they are, where people have generalized what Joseph and I and did and what we've done on Superstrata to include vector multiplets. And so you can add more degrees of freedom. I'm just taking, my goal here is to take the absolute minimal set of fields we need to describe precisely the supergravity dual of this kind of system. So the 1,1 theory, I don't know much about. Has anybody got anything they can add? Can you remind me what the exact question was? What happens with 1,1 theory when?
Well, the question was whether the projectors are compatible in the 1,1 theory. If you want to comment.
The 1,1 theory itself is defined by a single projector. So that just it's a first cutting in half. I'm trying to think what that must be.
Wouldn't the projectors be different for 1,1?
They will be, absolutely. And they won't necessarily be compatible with these. They will emphatically be different. They won't be helicity projections. They might be, I am not sure how best to describe them. They will not, because the whole point is that the minute you put these two down, it gives you the 6, 7, 8, 9, which tells you you've got to be, you've got a helicity, but you've got to use helicity in the. Oh, you know, I'm going to go right out on a limb and say maybe if you start with M theory and you go down on a circle into the 2A theory and impose, yes, and you impose the gamma 6, 7, 8, 9 condition, that's probably exactly what you do. Because the point is the original theory wasn't chiral. And so if you impose the toroidal projection condition I just imposed, but do it in M theory on a circle, so 2A, you will probably wind up with the 1,1 theory because the theory you started with wasn't chiral. It can't be made chiral by a chiral projector, I think. I think that's probably it. So maybe there is a way to go through the 1,1 theory to get here because, you know, you can go through the 1,1 theory and then truncate away that stuff. Either way, my purpose here is to go through the 2,0 theory simply because it's the most natural route through the D5 branes. The D5 branes and the D1 branes tell you to make chiral projectors on 2B supersymmetry. And so that's, for me, was the completely natural route to this. There may be a second, you know, there are other routes through M theory and compactifications of M theory. In fact, when Joseph and I were first doing this stuff, we used M theory and we used T6 compactifications to 5 dimensions. And then when we started uplifting back to 6. So we took a rather peculiar route through this initially. So I'm not saying this is the only route, but I'm just trying to take a route. And the content about the self-dual tensor gauge fields is going to be very important to us. I don't know whether I've answered the question, but
yeah, thanks.
Okay. Any other questions or comments? Okay. So if you simply look at this configuration, you just simply say, I want a D1, D5, and a QP, of course, you're going to get the 3-charged black hole. You just put in the sources for that, and you're going to get nothing. Nothing in the way of microstate geometries, I should say. So there's another sort of, I wanted to introduce this idea. We're not going to make heavy use of it. But while we're talking very generally about all this sort of setting of superstrata, I wanted to give you one of the tools we use to deduce other possible configurations that can be made compatible with the supersymmetry of the D1, D5P black hole. So in other words, what we're really looking for with the microstate geometry, remember, we're saying, I want something that looks like a black hole out from a distance, but is smooth in the middle. So what I really mean by that when I start refining it down is I'm going to take the D1, D5P black hole, the 3-charged black hole in 2B supergravity described by that system. And I want something with exactly the same supersymmetries. I want a BPS microstate geometry with the same supersymmetries. But if I just simply throw in 3 charges like this, I get the black hole. So what else can I do? There's a whole sort of way of thinking about this, which you can ask, what other charges you can add, what can you do, how can you deform the system in a way that doesn't break the supersymmetry? And this is critical to the idea of moving from the singular black hole solution to the smooth microstate geometry. And there are 2 very important versions of examples of this. One of which is I will calculate the hell out of this next time, But the first important example is the whole basis that Samir used in, I think, the original stuff on fuzzballs, and in particular, Luna and Mathur papers and so on, Luna and Maldacena Mars, which is where you start adding Kaluza-Klein monopoles and you add angular momentum dipole, Kaluza-Klein monopole dipoles, KKM dipoles and angular momentum. There's a way to deform the theory in precisely such a way that you still preserve the supersymmetries. And then there's going to be another version of this, which we'll see, which is where you can add fundamental strings. And so long as you add exactly the right amount of NS5 dipole moments as well. And so I'm going to sort of, we'll see this really when we solve the equations of motion. But for the moment, I just want to give you the sort of broad brush outline or way of thinking this can be very useful to see why this is true. So the sort of root cause of this, and I'll put some references in the notes about this. How do you see where these projectors come, these supersymmetry projectors come from? And it all comes from looking at the supersymmetry algebra. You start looking at commutators of supersymmetries and look at what the central charges are that turn up on the right-hand side of those commutators. This, if you go to a static frame, in other words, you drop the momentum and just call it the mass, and then this becomes zero. This becomes gamma zero squared. So this is the mass times the identity matrix. And then you get things involving the charges of each and every brane that you can have in the system, D1s, D5s, everything. Now, the point is, for the state to be SUSY, you've got this, there has to be some projector that kills the SUSY. And in particular, the pieces that turn up here tell you how to build the pieces that turn up here. And so, for example, where's the F1? You see that the F1, if you basically winds up sitting on the, sitting on the right-hand side of this beast. So the way that you deduce all this stuff is you start looking at the supersymmetry algebra, and the way you deduce the projectors, or what makes up a projector, is you start analyzing this beast. So all this to say is a very simple principle. It can be turned into a calculational principle. I learned this from Masaki and Jan de Boer. So if you start thinking about supertube transitions, we've got these supersymmetries, the D1, D5 system, for example. And now I want to throw in a possibility of adding this Kaluza-Klein monopole moment. And the Kaluza-Klein monopole, do I have this the right way? Damn it, I think, no, that's the right way. It's 6, 7, 8, 9 and 6, 7, 8, 9, but there is a special direction to Kaluza-Klein monopole, and then there's a possible profile that I can add. And I'm going to add a momentum generator. But it's called an angular momentum generator because I'm thinking about this as being a momentum generator going around a loop defined by a parameter theta. And so,
Can I stop for a second?
Yeah, sure.
There's another way to think about the Kaluza-Klein monopole. So the point is, if you take a Kaluza-Klein monopole along these directions,
yep,
and you basically see this Kaluza-Klein monopole as an object in 11 dimensions, so you just multiply by another dimension and you uplift.
So D6.
What you find is that the Kaluza-Klein monopole just means you have a hyperkähler space in the transverse space.
Yes.
So Kaluza-Klein monopole in the direction 6, 7, 8, 9 theta. Okay. 5, it means that this actually is the same as gamma 1, 2, 3, 4.
Okay, so can you hold that comment for a second, because I've got a very particular way I want people to think about this.
Okay.
So the point is, these are if I'm just thinking about the D1, D5 system, I've got these projectors, and I just have them from, well, in particular, I've got this projector. Now I'm going to throw in two projectors, and this projector is not compatible with either of these, or neither is this. This guy will basically gamma zero commutes, but the gamma theta anti-commutes and so forth. So this projector does not commute with this, it doesn't commute with this. Similarly, this projector doesn't. But together, done in the right way, the difference of these projectors is in fact 6, 7, 8, 9. So the sort of thinking here is that you can add Kaluza-Klein monopole configurations and angular momentum configurations together so that the only thing that survives the projection is that thing, which is something you've already got. So let me sort of say this in words, and I'll draw a picture. So the one way you can understand what is sometimes called the supertube transition, and if this isn't clear now, it will become clear in the next section when I start going through all the ways in which you make the superstrata, and we will build the Kaluza-Klein, we will build this supertube, simple supertube. But you start with D1, D5, but now you can add Kaluza-Klein monopoles and angular momentum. And you can put it around any old curve parameterized by theta, and you can arrange it in precisely such a way that it preserves the supersymmetries, so long as these two quantities are tuned to be matching each other in exactly the right way. And so let me, as I say, give the prime example. You start with exactly what I have. You have some D1s and D5s, they're wrapping, I've called it the Z in this, I ripped this out of a different talk, but Z, and then the T4. And you have these two projectors. But what I want to do now is I want to actually add some angular momentum and spin it out around a curve. So now I actually smear the whole thing out along this curve, and there's an angle theta, and there are more projectors to be thrown in because I've now got angular momentum and Kaluza-Klein. But if you go through that projection condition and ask, what is it? The numbers that turn up here are the charges of the Kaluza-Klein monopole moments and so forth. But if they have a certain algebraic relation and can be parameterized in exactly the way I've described, then what happens is this projector, which consists of momentum, it consists of a momentum projector, and also this is the D5 projector, this is the angular momentum projector, this is the Kaluza-Klein monopole projector. So if the configuration has all these charges, but with exactly the right tuned coefficients, the projector can be written as a linear combination of the D1 and D5 projector. And so as a result, even with an arbitrary shape, this gamma z theta is totally incompatible with the D1 and D5 projectors, but it doesn't matter. The pi will still kill the supersymmetry, precisely because it can be written in terms of D1 and D5. So the whole point, the sort of moral message of this story is you may have projectors that look utterly incompatible with the thing you've got, but if you add them with the right mixture and with the right coefficients in the right way, you can arrange that that configuration has exactly the same supersymmetries as the state you first thought of, because the corresponding projection condition it adds is a linear combination of the projection conditions you've already got. And we're going to see this thing in great detail when we, the very first example I will, well, actually the first example I'll do is the D1, D5P black hole. The second example I'll do is exactly this one. So when we solve the differential equations, but the rule of thumb is you don't necessarily want to think about discarding configurations like angular momentum or Kaluza-Klein charge because of incompatible projectors, because there are ways you can combine them. And here are the offending ones, which are incompatible with these guys. But if you combine them in exactly the right way, you lock the angular momentum charge to the KKM charge, then it can actually still be supersymmetric. So Joseph, jump in if you like.
Nick, can I ask a question?
Sure.
So the way you've written it, the fact that it turns out that you can take the difference between the KKM charge projector and the angular momentum one,
right?
The linear combination of the D1 and D5 ones.
Yes.
Does it just mean that you were just unaware of the option to add angular momentum and the KKM charge?
Well, if you just added angular momentum KKM charge unconstrained, you would break all the supersymmetries. And that's because this projector of the KKM and the projector for angular momentum are incompatible. And moreover, the minute the theta direction, this theta direction is standing in for a curve, a tangent to any curve. And the minute, a priori, if you add a projector whose direction changes, you break every piece of supersymmetry there is, because there's no consistent projection in that direction if the direction changes. But the beauty is that if you do it so that you tune the offending supersymmetries in a particular way, in other words, you lock the KKM charge to the angular momentum in exactly the right way, then you can do it in a way that preserves the supersymmetry.
Yes, I know that. My question was more like, do we know whether it's possible that there might be some other combination of projectors that you can add in a
Absolutely. And so this is a game Joseph and Masaki and Jan de Boer and lots of people have played. I mean, we're not the first, but what I wanted to point out, it's a very important principle. So if you read Porcinski's book, there's this beautiful list of projectors in it. It says, look, you throw in these branes and it breaks the supersymmetry in these ways. But then we came to realize there are much more subtle ways that supergravity has of preserving supersymmetry that look on the face of it that they violate Porcinski's simple rules. But they dodge the bullet precisely because they take the offending, apparently incompatible supersymmetry projectors and combine them in ways so that it does not break the original supersymmetries. So this is
a systematic way to study what you
there is a systematic way. In fact, we discovered Superstrata by simply asking this question as generally as we could for the D1, D5 system. And we discovered that there had to be things that went beyond. Well, this is Samir's example. This is the lunar Mathur story. You take D1s and D5s, which a priori is singular, and you can desingularize it. And we're going to solve, write down the solution to this system. And we'll see it's beautifully smooth. It's global ADS3 times S3 if this is a circle. So whether there is a systematics, sort of, how to put it, there's lots of projectors and there's large numbers of combinatorial ways you might think about messing with them. So you can start, if you have a particular brain system in mind, you can try and do an exhaustive search of all the options. And there are other things you can do. Masaki is really the expert on this, and that's probably something that, obviously Jan, but Masaki's written several papers on this, and he has these things about, I don't know, is Masaki here? It was expected to be here, but he has these other exotic brains which you can throw into the mix.
There's double supertube transitions which you can do, and so on and so forth.
So what I'm trying to do in this lecture is trying to give you the big picture of some of the ideas that go into this. And because I was thinking, I don't want to dive into solving differential equations, that's next time. But for the moment, I want to give you one of the sort of core ideas that without doing any supergravity calculations. And one of the core ideas here is that if you go to Polchinski's book and just look at supersymmetry projectors, it suggests that there are very few things you can do. And in particular, if you get the D1, D5 black hole or the D1, D5P black hole, you say, I can't add anything else to that because the projectors are incompatible. The message here is, if you combine incompatible things in the right way, you can make things that are compatible. And the lunar Mathur story is one absolutely beautiful case of this. So, Joseph, did you want to add something?
No, so just one thing, Masaki's configurations can be, so this game can actually be played with much more complicated brains. You can do like, 2 NS5s and so on and so forth. The thing is, D1s and D5s are nice because the objects into which they pop up are actually nice, decent D brains. If you do, for example, 2 NS5 brains, which are mutually supersymmetric, then they pop up into this horrible non-geometric.
One second. You're just using a technical term, pop-up. The pop-up means what can I add that's compatible with them in this way? So go ahead. Pop-up means yes.
So essentially, if you look at the system of 2 NS5s, they actually pop up into something which is non-geometric, horrible, the kind of stuff which people who do flux compactifications like about these non-geometric backgrounds and so on and so forth. There's a whole slew of them and so on. Now, luckily for us, for reasons which I have no idea, and if you ask me why this happens, it was just, sheer luck. In the D1, D5 system, it so happens that this popping up is actually into this KK monopole, which is a nice, happy object. It's a smooth object. And we thought for a long time that this popping up is going to give us some non-geometric things, and all the black hole microstates are going to be non-geometric. And for a long time we were depressed about the future of this program. But somehow, we turned out to be amazingly lucky that in the D1, D5 system, everything is nice, everything is smooth, everything is supergravity. There's nothing non-geometric, there's nothing singular. And again, I have no idea why we were so lucky, but
it really does work that way.
Yeah.
And so I wanted to raise that as a point. When we start solving the differential equations, we're going to get answers and results. But I wanted to have a framework where I can say, oh, remember what I said back then about, oh, here's the Kaluza-Klein monopole charge, here's the angular momentum, here's the next thing I'm going to say is there's another version of this, a variation of the game. Now, I'm not going to go into this. Sorry?
Can I ask a question about
sure. the
previous one?
Yeah.
So it's a silly question. So this KK monopole and the angular momentum charge, are they quantized in some sort of fashion, or like can you think of one unit of?
Of course.
Or?
Yes, the angular momentum is certainly quantized, as is the dipole charge. Yeah.
Mm-hmm. All right.
And so the kind of condition you have is that, correct me if I'm wrong here, but Q1, Q5 must be equal to, was it J times is it J times K, Joseph, or is it J times?
So there are two things. First of all, so when you have momentum along some direction, the quantization, so what's happening is that you have some units of momentum which are quantized. You have 17 units. If you make that direction double the size, what will happen is that the momentum quanta are going to have half the momentum, and moreover, you are going to smear them over twice longer region, and therefore the supergravity charge of this momentum quanta is going to go down by a factor of 4. On the other hand, if you make the circle twice bigger, the KK monopole is going to stay the same. So in order to get these projectors to actually cancel in supergravity, in order to get the KK monopole and the J to be very friends, you have to be at a certain radius. If you just make them, if you just stretch this thing more, what you find, you dilute the momentum or the angular momentum, and you keep the same KK monopole. So then the killing spinors are going to twist into being non-supersymmetric. So supersymmetry is really crucial about you really have to have a local balancing of the momentum density and the KK monopole. That's all you have.
So another reason why I'm sort of bringing
and that's all supersymmetry. There's something else then. You can also have smoothness. And then there's a condition between how much D1 density, how much D5 density, and how much momentum density, how much KKM density you have. But that's a different condition. That's a condition essentially that that everything is smooth locally. But the supersymmetry is just you can have. It's just about the J and it's just about the J and the KKM being happy and canceling each other.
So there are two reasons why I'm putting this idea out there. Is that this is the mother of fuzzballs and the mother of microstate geometries, in the sense of you start with something which is manifestly singular. It's a two-charged black hole. But by adding and allowing yourself deformations that preserve the same supersymmetry, you can make this turns out to be a smooth geometry. So this kind of transition, this kind of option to add stuff and not break supersymmetry is the key to going from the singular configuration to the smooth configuration. Without this option, the whole microstate geometry program wouldn't exist. And so this is Samir's, I think, early observation that really this system, when you back react it, the actual holographic system is this. And I'm probably doing injustices to many other people who worked on this, but Kostas Skendaris and of course Marika comes immediately to mind. But the basic heart of microstate geometries, the motivation that started the whole game with fuzzballs was this kind of observation, that there are smooth things in the same supersymmetry class as the singular things. And these are the better holographic geometries. But the point is that I think it was Bogdan asked, I said, there are lots of options, and we discovered Superstrata by pushing. We asked ourselves, if you have D1, D5P, what are the things you can do here? We wrote a paper, the first paper sort of said, it's called double something or other, the Supertube bubble or whatever. The point is you can do this transition twice. I don't want to go too much into detail about this. I just wanted to point out to you that even within the sort of naive Brane physics, without doing any supergravities, you can see the beginnings of these options of adding more geometric features and still keeping the same supersymmetries. The smoothness, of course, is not apparent, but you can see this possibility. And as Joseph alluded to, and what this equation tells us is that this is the D1 charge, this is the D5 charge, this is the angular momentum, and this is the KKM charge. But these coefficients are locked together, and that locking together relates to there will be parameters in the solution that are in fact emphatically locked together. We'll see how the KK monopole charge and the angular momentum have to be locked together, and also the smoothness conditions will give you these kinds of constraints. So at some point I'll say, look, here's the Kurzgesagt monopole, here's the angular momentum, here's how they're related, and then here's the smoothness condition, and it will be precisely to implement this procedure. Now, there's another very important example, which I'm not going to go into in detail, but it's in the same flavor. But it's actually got some interesting physics in it, which I don't properly understand. So if you take the D1, D5 system and the momentum system, so now we're going to do it with all three beasts, you can ask the question, well, let's look at the fundamental string. Can we add fundamental strings or NS5 branes? They're dual. And basically the answer is, well, this is fundamentally incompatible with this, and this is fundamentally incompatible with this guy. Sigma 1 and sigma 3 do not commute. So this looks like a disaster. But the whole point is, roughly speaking, that there's a sort of difference, which is once again 6, 7, 8, 9 between these two guys, and there's a common factor which is gamma 0, 5, and you can implement the same procedure. What it says is you can make configurations of fundamental strings wrapping the 5 direction or moving the 5 direction, and NS5 branes, so long as you tune this and this to be locked together in a certain very specific way. And if you do that, you can actually preserve the same supersymmetries as the D1, D5 system. So there's some strange statements. This is, in a sense, supergravity-wise, comes out just in your lap. But from the point of view of string theory, this is a very strongly non-perturbative statement. It says, look, I want to throw in some strings into this configuration. And it looks totally hopeless. It looks like it's going to break all the supersymmetries or break some more of them. So you throw this in and you say, well, okay, that doesn't like this. This thing hates this thing. It hates this thing. It's okay with this, but I don't care. But it's screwing up all of this. So, but there's a non-perturbative thing. This is order G string to the 0. This is G string squared kind of effect. But if you add them in exactly the right combination, you can actually keep the same supersymmetries. And we'll see this occur. We will turn on the B mu nu field in 2B supergravity in precisely such a way that it still preserves the supersymmetry. So there are loads of examples of this, and the sort of hint that you might be able to do it is if sums and differences, or sums and differences, if the factors in this kind of supersymmetry transformation have differences that are compatible with things, then you might be able to play the game of tuning so that you get another supersymmetric configuration. This is a huge subject. I just wanted to touch on it to say that the naive impression you get from Pociński's book is this is the law about supersymmetry when you have branes. It's not true in the sense where it's true. What he says, of course, is absolutely true. But the point is, it's too naive just to slap down projections and say, oh, that breaks all the supersymmetry. If you tune the configurations just right, you can actually keep the supersymmetry you already had. Okay, so the whole point of this thing, the whole point of this projector analysis is that it actually informs the sort of geometric features you can add, and it informs the sort of excitations of the system you can add, and so forth. Okay, so coming back to where we're at, I want to actually tell you the system we're going to actually start analyzing next time. We're going to have basically 1, 0 supersymmetry, with two tensor multiplets. It's going to have a graviton. Well, we're only going to care about the bosons. It's going to have a graviton, a self-dual tensor field, and two self-dual tensor fields, two anti-self-dual tensor fields. Now, where does it come from? So I'm going to go back to the beginning, and I'll give you this full dictionary. Once we've started making solutions, I'll tell you how they turn into 2B solutions. But it's going to illustrate some of the points. First of all, obviously, the graviton goes to the 6-dimensional graviton. But here's the thing, it highlights what I just said. One of the things we're going to keep in this, one of the things we have in one of these two anti-self-dual tensor multiplets is the anti-self-dual part of the Cal-Ramon field, the B mu nu field. The anti-self-duality is required by supersymmetry. But if you think about it for a minute, the Cal-Ramon field is, of course, sourced by the F1 NS5 system. So I'm telling you that the system, this supersymmetry system, contains the field that's sourced by F1 and NS5, but it's required by supersymmetry to be anti-self-dual. That's the statement I just made. I said, look, you can throw in F1 and NS5 so long as they're tuned together in precisely such a way to preserve the supersymmetry we first thought of. And this is what happens. It's required to be anti-self-dual. So that's, and then of course the rest of it's kind of obvious. There's a scale that can turn up here, but supersymmetry locks it to some other scales. Then of course the other obvious thing, we have the C2 field. It's unconstrained in duality when you descend it. Or you can think of C2 and C6 as encoding the self-dual and anti-self-dual tensor gauge fields. But basically this is the D1, D5 system. So basically we have the D1, D5 sources, and we have the possibility of adding F1 NS5 charges that are set equal. Go ahead, Joseph.
No, it's just that you can see that you can put some F1 and NS5 charges, not equal ones, but you can put some of them by doing a partial S duality. So if you have some F1s and some, if you have some D1, D5 system, which is again polarizing into a KK monopole and angular momentum, when you turn on, when you do an S duality, you can do a partial S duality, then some of the D1s are going to become F1, some of the NS5s, some of the D5s are going to become NS5s, and you still have the same KK monopoles. And because you have the same KK monopoles, you can see that this is going to be compatible with gamma 5, 6, 7, 8. That's all.
Okay. So, so the last gasp of this is going to say, remember there was a stupid scalar coset? Well, it turns out that it's going to be there, and the coset that we're going to be working with is something you knew had to be there essentially from 2B supergravity. So we have the dilaton and axion remaining. All the other scalars that can turn up get locked to the dilaton and axion. We have an SO12 over SO2, but it's just the coset that was there in the original 2B theory. So all this to say is that the interesting theory in question is essentially the graviton multiplet with precisely the tensor gauge field sources of the D1, D5 system, plus the possible adding of the B mu field only in its anti-self-dual form. And the count is, I said, 1 self-dual and 2 anti-self-dual tensor multiplets. Well, the self-dual guy and the anti-self-dual guy, the self-dual and anti-self-dual parts of this, plus the anti-self-dual part there. So there's an SO2-1 symmetry, and the scalars exactly reproduce that. So really, this is, without this, this would be the bare bones of what you need for the D1, D5 system. But adding this is actually critical to making superstrata, absolutely critical to making superstrata. So this was the new ingredient that we really, really needed. And we're going to talk all about why it's there later. So that's sort of where I absolutely really wanted to go. I've got other remarks I can make. I think the next slide is just, yes, a place marker for me. Any questions? Because what I will do next time is I will start with this theory in 6 dimensions, and I will start analyzing the BPS equations.
Yeah, it's just to confirm one question. So n equals to 2 for the number of tensor moods is chosen so that we work in type 2B, sort of like, if we choose another n, then
Yes.
then we would not have like come from time to B.
Oh, no, okay. If you choose n up to 5, you will be in the toroidal compactification of 2B.
Oh, right, yeah.
Where did the other tensor multiplets come from? I'm going to explain that in great and glorious detail, but basically what's happening here is that the tensor gauge fields we get are the ones that are sort of given to us by the gods in 2B. They are the Kalb-Ramond field and C. So what I've dropped out of here are all the 2 index tensor fields you get from taking C4 and writing it as a 2 form on the T4 and a 2 form in the space-time. All of those have been dropped. But I have.
Is it a choice, simplification choice, or
it's a simplification choice? But if I took n as 5 here, I would include everything that I get from here. But this is a choice, and the choice is being made for the following reason. So let me back it up. I'll say much more about this once we have some actual solutions to talk about. But the basic point is that we absolutely have to have this because we want to talk about D1 and D5. This is given by, but we could throw in any number of other tensor gauge fields obtained either from the Kalb-Ramond field or from the 4 form descending into 2 form times 2 form. And you could throw any of those in, and in fact, you can make superstrata with, and where do you get n is 5? Well, you've got, basically, this gives you n is 2, and you get 3 more because a priori, there are 6 2 forms on the torus, because it's 4 choose 2, but you have to impose a self-duality combination, so that gives you 3 more. So I've explicitly thrown away the 3 more, but if you want to do that, you can put this to n is 5, and if you do K3, you can put n is 21.
Right, yeah.
So you can do as much as you like, but there's a very good reason for doing this, or 2 good reasons, which I sort of swept under the rug. First and foremost, there's an exercise. When we first started trying to make superstrata, we did not have the Kalb-Ramond field. We just simply had the crude infrastructure, and in fact, it was the n equals 1 version of the story, and n equals 1, you lose the dilaton as well. So and the coset is SO11, and it's just sorry, you keep the dilaton, you lose the axial. So we started trying to make superstrata that way. It turns out that it's not possible to make smooth superstrata. It turns out to make smooth superstrata, it's absolutely essential to add this. So the history of this subject has been driven very much by our friends and sort of, Rodolfo and Stefano and Masaki and David and so on, telling us that string theory tells us we have to activate certain degrees of freedom. Otherwise, we don't get sensible answers in the holographic dual field theory. And this was very much a message from Stefano and Rodolfo that said, you're not going to get, or actually David as well, going to get a consistent supergravity dual to the CFT unless this degree of freedom is activated. I thought, well, why do we need it? But we couldn't make smooth solutions. So we activated it and it suddenly all just worked beautifully. So the history of this is we usually pare down to the absolutely essential degrees of freedom to describe the physics we want. And then we start adding stuff when we need to, or when the conformal field theory tells us to do so. Now, a priori, my prejudice is if you extend n to 3, 4, 5, and so on, roughly speaking, this thing contains a particular class of excitations, and adding more of them just adds more of the same kind of excitation, roughly speaking. So what you're doing is you're increasing the phase space, but not capturing a priori any exciting new physics. So doing what we usually do, we try and work with the smallest theory that's going to give us the physics we want. And then occasionally we get bitten in the arse and we have to expand the phase space a bit. For a good example of which is the recent paper with Emil and Stefano Masai and David. They've started activating another one of these tensor multiplets to describe another class of strings. So I'm freezing out as much as I can so that I can get to superstrata without adding any other bells and whistles. But adding more tensor multiplets adds more bells and whistles. Mm-hmm. The second thing is also what's hidden here is we know exactly the holographic dual states for this system. Very, we kind of have it down. Adding more stuff, we move into a territory where the holographic dual may be not so cleanly described, although, as I say, Stefano, Emil's, and David's new paper is all about adding yet another tensor multiplet for which the holographic dual we now understand. So it's a good question. We can add more tensor multiplets, absolutely add more tensor multiplets, but it's sort of adding more decorations on the essential core of what the superstratum is. Put another way, it's exploring more of the conformal field theory phase space. But to get to where I want to get to, this is what I'll need. And the startling thing for us a few years back is that we needed this. We didn't think it was necessary, but it turns out this is essential. And Stefano and Rodolfo discovered that by simply saying, look, let's look at some string scattering amplitudes and look at what a closed string does when it hits a D1, D5 system, what fields, what states get activated. And they said, you've got to turn this on. Otherwise, it just doesn't make any sense. So we did, and suddenly we got stuck in making superstrata, and suddenly it all worked perfectly. And that leads into a whole other story, which I'm not going to talk about. Every time we do a supergravity calculation and make a microstate geometry, we make predictions about how certain supergravity constants and coefficients and moduli get locked to other supergravity constants, coefficients, and moduli. And smoothness tells you that you have to make a lot of constraints, or things called coiffuring constraints. So just to take these degrees of freedom and turn it into a smooth geometry. But every time you make such a prediction, it's making a prediction about an amplitude that you can, in principle, compute in the CFT. It's telling you that certain correlation functions must be related to each other. And David, Stefano, Rodolfo, Masaki, and so on have done some of these remarkable precision holography tests, and they work. We made some definite predictions about certain coefficients that came from smoothness and supergravity, and they fall right out of the corresponding CFT. So this is an immensely powerful principle. And the first lesson we really learned from the CFT people was that we were missing a critical ingredient. And now we've put this back in, we can make predictions about what this ingredient has to involve and how this ingredient feeds into these ingredients, which tell you about correlation functions. I think the precision holography of this system is really highly developed now. I don't know, Stefano, I think was here earlier. You may want to add something. So,
no, sorry.
Go ahead.
You mentioned my name, or
I just said, Savannah, I was talking about precision holography in the context of these sort of D1, D5 systems, and just thought maybe that.
It's another Stefano. So,
sorry?
It's the other Stefano.
No, Stefano Masai. I was just thinking about your recent paper with David and Emil. It's again a statement about including yet more degrees of freedom as required by understanding the CFT.
Right, yes.
So,
I'm here, but the connection is so bad that I am, I don't know if, yeah.
it might be,
yeah.
it may be that we have to shut down videos in future, but okay.
Okay. Yeah.
Given the hour, I might save the discussion of symmetries for another time. But one of the things I just wanted to make is, this is more a historical comment that I want to finish on. So when we were first doing these microstate geometries, we first started 15 years ago working in 5 dimensions, and we managed to make a whole bunch of microstate geometries. So I want to just connect to that. And the whole point is, it's the usual story. If everything's independent of the 5 direction, you can do a dimensional reduction. And basically, the 5-dimensional metric gives you a Kaluza-Klein field and a scalar. The unconstrained tensor gauge field reduces to a vector and another tensor gauge field, but that can also be reduced to a vector. So each of these tensor gauge fields produces 2 vectors. Or equivalently, a self-dual or an anti-self-dual tensor gauge field produces a vector field. So at the end of the day, this 1,0 supergravity coupled to n tensor multiplets gives rise to n equals 2 supergravity. It's n equals 2, which means 8 supersymmetries. So it's n equals 1 in some other sense. Anyway, it's got 8 supersymmetries coupled to n plus 1 vector multiplets, which was the sort of starting point for all this sort of thing. And notice that little n is 2, 3 tensor multiplets corresponds to precisely coupled to 3 vector multiplets in 5 dimensions. So I think I've got that right. So we will talk about that in data, but this was sort of the historical starting point. When we first started making microstate geometries, we started in 5 dimensions, and we started working with n equals 2 subgravity actually coupled to only 2 vector multiplets. And the extra Karl-Bramon field that we needed actually said you've got to actually include yet another vector multiplet. But that's really the 6-dimensional story. And this is what I also wrote about in those other lecture notes. We're not going to reduce to 5 dimensions in this thing. We intrinsically want to work in 6. And there's a very simple reason for that. The superstratum that we're going to be talking about has momentum waves traveling up the y direction. And the y direction is the 5 direction. So the really interesting solutions that we want to make critically depend on this direction and cannot be reduced a priori down to 5 dimensions, although there are some tricks to do that, which we can talk about later. But morally speaking, the solutions we're building or going to build are intrinsically 6-dimensional because we want to have momentum waves traveling along the 5 direction in order to create these microstate geometries. Okay, I think my voice is giving out, and I should just let me stop sharing and just sort of field questions if there are any, or any concerns or comments. And as I say, next time my plan is to start actually talking about the precise 6-dimensional theory, writing down its equations of motion or BPS equations, and talking about the underlying geometry and actually beginning to solve equations and writing down BPS conditions. And then I want to get into the weeds to show you where the bodies are buried in terms of calculating stuff. This lecture was meant to be sort of, here's the bigger picture of the ideas involved. I hope it worked. Anyway, questions or comments?
I'm very happy. You guys should be saying stuff.
So as I say, the title is Constructing Superstrata. We will construct them, but the very first lecture, it's meant to be, here's the bigger picture of how it fits in with everything else, and here's the theory and why we're considering this particular theory, at least from the supergravity perspective.
And also to understand, because, I mean, doing supergravity blindly without understanding the d-branes, it's always like, you don't know what's going on. So, it's very important to understand what the d-branes are, what their physics is, why can you add this ingredient and the other one you cannot, because if you just go blindly looking for solutions, you'll end up nowhere. So
yeah, it's it's the usual conundrum. There are lots and lots and lots of solutions you could imagine building, but the real issue is what's the ones that are going to teach you the most physics. And there are actually 3 legs upon which this stands, and one of which is you kind of need to know the supergravity, and that's what I'm going to focus on in the lectures. But it's highly, highly informed by the d-brane physics. You must understand sort of the underlying d-branes and what you're adding to the d-branes. And then the third thing is, which I'm not very expert in, but is I hope it came across, is that a lot of the supergravity calculations are deeply informed by what we know about the dual CFT. And so that's a huge injection of telling you what kind of degrees of freedom you have to activate and how you should activate. And as we go, I'll hopefully sort of point out some horrible unsolved problems.
Hi, can I ask a couple of questions about the general thing? So well, the first one is about, again, this adding this KK monopole and angular momentum the solution by making it smooth. Now, so we start from D1, D5 black hole, and then I open up the. So is that going actually in a gauge theory language to the Coulomb branch of the theory? So like separating the branes and going into the Coulomb branch, or we are still in the so-called Higgs branch, roughly speaking? There is any
Higgs branch.
We're still in the Higgs branch.
You're not separating the branes. The branes are remaining in a thread. So you're certainly not separating the branes. So it's not a Coulomb branch.
I see.
You
can see that we know the CFT duals. So if you look in the CFT dual, all the states, they correspond to bound states of D1s, D5s. The Coulomb branch corresponds to unbound states where you can take them away.
Yeah.
These guys you cannot take away. They form a bound state. And then if you try to make this bigger, you find that it doesn't want to. So, they are basically forming a bound state. That's how you distinguish Coulomb branch from Higgs branch.
Yeah, thanks.
So another way of putting it is when the D1s and D5s together, there's a huge central charge to the conformal field theory. And essentially, the Ramon ground state is highly, highly degenerate, degeneracy order M1, N5. And then the sort of shapes and excitations you can put on that have to do with the different highly degenerate Ramon ground states in that system. So it's critical that all the branes are on top of each other for that to be.
And is that in a certain sense more typical than the previous solutions where you don't add any of these charges and so on? So what about very naive one, but what about typicality of these solutions?
Okay, so D1, D5, okay, this is a much more difficult question when you add the momentum, but in the D1, D5 system, I think Samir made a pretty compelling case that and particularly through Costas and Marika's work also, that the sort of the ground state structure of the D1, D5 CFT is beautifully represented in the geometry of the KKM monopoles and so forth. Did you want to add something, Joseph?
So in the D1, D5, we know the counting. We know very well, and essentially, you can show that all the typical states correspond to this kind of big configurations. That's something which is known. In the D1, D5P is not known. But there's something about Coulomb branch which I also want to discuss. There is a misnomer. People call Coulomb branch in other system of bubbling geometries. People sometimes call Coulomb branch the multi-center bubbling configurations. This is wrong. Just because something is big in the transverse space doesn't mean it's Coulomb branch. To be on the Coulomb branch, you need to be able to move without, to have a flat direction and to be able to go to infinity. So something which cannot escape to infinity is not on the Coulomb branch. That's basically this is the intuition. Now, what's happening in the field theory is very subtle, because on the field theory, if you look at the Higgs branch, it corresponds to configurations of D1s and D5s, which are basically just doing stuff on the internal manifold. All the Higgs branch stuff has zero size in the transverse direction. However, what's happening is that there's a wave function which is localized on the Higgs branch, which has a leakage on the Coulomb branch. And when you go to supergravity, whatever leakage you have on the Coulomb branch actually gets enhanced and becomes very large. And all these Higgs branch states become visible as big fat supergravity configurations in the transverse space. This is undergoing intuition.
I see.
And we know it very well from the D1, where it's beaten up to death. And there are some other examples when it's known. So what actually happens is leakage that Josef's referring to, the field theory, when you turn off the sort of gravity interaction, it becomes all these sort of delta functions, and the Coulomb and Higgs branch meet at a point. But when you have the gravitational back reaction, it actually gets smoothed out. And this leakage Josef was talking about is precisely that the Higgs branch really does have some influence on the geometry that looks Coulomb branch-like.
I see. That's very interesting.
But the hint that it's sort of Higgs branch leaking on the Coulomb branch is precisely that there's some rigidity to it. In other words, it can't spread arbitrarily far. We call them the bubble equations, but there's some limitation on the ability of the branes to spread caused by the detailed dynamics. But we do see it. There's some discussion of this in some early papers of Jan de Boer and Massima and Shiro Shook, and I'm missing somebody. Anyway,
Dieter van den Bleeken.
Dieter van den Bleeken, yeah. And so they look at the Higgs branch states, and then they show that there is actually some sort of Coulombic leakage.
No, that's actually our paper with Micha Berkuz and Jan Scheer.
Good. So.
And also a very last naive question as well. And what about doing this kind of studies also in the case of D0, D4, so in type 2a, when you reduce to a 4-dimensional black hole and then you try to do the same procedure and try to, resolve the singularities?
Yes, I think that's your department.
The D0, D4, if you look at the configuration into which it puffs up, it's an NS5 brane. Now, NS5 branes are lovely, but the problem is it's very hard. They're not smooth. So it's very hard to ascertain that, something is good. And, when you go next to an NS5 brane, the dilaton is very unhappy. The curvature is very unhappy. So it's very hard to keep control on the physics. And then you can just say, oh, I have an NS5 brane, it's singular, but I'm accepting all the singularity I want. If you do that, you can overcome the black hole entropy. The whole game is to find configurations which are smooth and have they have the same charge as the black hole. And then NS5 brane, it is very nice, but it's not a good duality frame in which you can do calculations. That has been our experience. Again, the black hole exists in all the possible duality frames: D1, D5, D0, D4, D2, D2, M2, M2, M2. In all the possible duality frames the black hole exists, the entropy is always the same, however much you dualize the black hole. However, it looks like this D1, D5P duality frame is much, much better for understanding the microstates and for actually finding smooth solutions than all the other ones. And
unless you have a worksheet description, maybe when you have the
the problem is you also have D0s and D4s. So you have Ramon fields.
Yeah.
So then you have to do Berkovitz formalism. I mean, it's basically opening up a can of worms. Essentially, people are trying to stay away from it. That's basically it.
One thing I will say is in the two-charge system, there's this beautiful sequence of papers that Emil and David and Stefano Masai have been writing, which is using or pushing as far as you can within the worldsheet formalism, but they have the advantage of only looking at F1 NS5, so it's all locked into essentially the Never-Schwarz sector. So if you work there, you can do a very, very remarkable sets of calculations in worldsheet formalism, and it's beautiful stuff. But it doesn't quite.
Actually, in D0, D4, what's happening is that all these KK monopole shapes, if you T-dualize D1, D5, the KK monopole is going to become an NS5 brane, and you'll get all the shapes. So the shapes exist, also in the D0, D4 frame. It's just that they're very hard to trust, and it's very hard to do calculations, and it's very hard to build on them.
Right. So put another. I remember historically what happened was that we were looking at how to, literally using this sort of D-brane thinking that I was describing. We said, okay, we know we got three charged black holes. How many ways can we deform it in such a way that it's consistent with the supersymmetry? What charges can we add? How can we add more branes, more configurations, more fluxes? And so Masaki, very much an expert in this, he sort of took us through all these sort of bubbling transitions and dipole transitions. And we were sitting going through them, and we were getting depressed because it looked like every one of them was singular. And then Joseph put his finger on the board and said, this one is smooth. And it was the D1, D5P system. The D1, D5P system has this remarkable feature that even though all these...
Actually, you realized it wasn't me.
Okay.
I still remember the phone. Nick was in California. I still remember how we were on the phone, and he said that, and the codimensions, I believe it was codimension 2, like the D7 brane with logs and stuff, and Nick was saying, no, something doesn't work, and then, we realized it's codimension 1. So, that was actually...
Anyway, so it was a beautiful story, but the broader point is, what Joseph says is you can T-dualize everything or dualize everything to any brane configuration you like, but it turns out there seems to be only the D1, D5P system that things are smooth geometry. And that has a huge advantage because you can really analyze the holographic duals and the holographic states of that system much more effectively. Once you've got singularities, you start having some difficulty knowing what to do.
Okay, that was super clear. Thank you very much for this.
Oh, you're welcome. Any other questions?
Hi, Nick. Just an easy technical question.
Sure.
When you have these objects, you realize you can mix with the original supersymmetries like F1 and S5 dipoles and KK monopoles and momentum. are there restrictions to use them at the same different of them at the same time? Do you get extra conditions?
No, not sure I understood the question. If you just throw in F1 charges, you're sunk. You break all the supersymmetry.
No, but if you add for example, can you use both an NS5 F1 dipole and a KK monopole?
Yeah, that's exactly what a superstrata does, actually.
Okay.
So, but the broader question is a very, very good one. That this is the process of adding stuff is an imprecise science, and both of them sort of feed off each other. I mean, if you just simply say, "Here's the theory I want," it's n equals 1, supergravity, whatever. You say you can set about solving the equations of motion, and you can set about solving, seeing if you get smooth solutions. And sometimes you find these miraculous things where you say, well, where the hell did this smooth D1, D5, P, KKM thing come from? And then you can go back and say, well, it obviously comes from this transition in these branes. And these two approaches fuel each other. You find smooth solutions you didn't expect in supergravity, or very much the thinking in Superstrata was, there must be something else that I can add to this system that somehow makes a much larger phase space of smooth geometries. And so using that D-brane geometric transitions thinking, we came up with the ideas of doing Superstrata. So I injected into this first lecture because it's a tool that you kind of should know is out there. I won't use it anymore really during this thing, but as a reference tool, it really is a very nice way of thinking, because in this game, there's so much supergravity schlock that you can dive into. There are so many things you could imagine trying to solve, so many equations you could imagine trying to, or degrees of freedom you could imagine activating. But it's a very, very powerful tool is to understand in terms of the D-branes what you're adding, and then also in terms of the CFT, what are the states of that CFT that you're trying to activate. So having that as a reference frame on which to look at things is a very useful tool. So that's why I injected all this stuff in the first lecture. The next lecture, as I say, is here's some supergravity equations. We're going to set about solving them. But I wanted to give you the sort of broader brush of here's the supergravity, here's the D-brane thinking, and I'll leave it to somebody else to talk about the CFT thinking. It's very powerful, but for me, I just have a lot of good friends who do this very well, and a couple of postdocs who do it very well as well. So I can pound on them when I need to know some CFT. But this is an art, to some extent, an art form. Really, the whole story of Superstrata is answering the question you just asked. What can I add to a known supersymmetric system in such a way that it doesn't break the existing supersymmetry? That's what Superstrata are. That's what the microstate geometry program is. It's, can I take the existing black holes and deform them into a much, much larger moduli space of smooth geometries? And there are ways in which you can infer how you might do that. And one of these ways is this D-brane process. There's another geometric way of thinking about called geometric transitions, which we may or may not get to. So that's really the money question. There's another sort of confessional thing we need to make, which is the following. I said that for the D1, D5 system, when you add the KKM and the angular momentum, there's a beautiful correspondence between the states of the ground states of the CFT and the shapes and so forth that you can put on these profiles. And that seems to work beautifully. And this is the work Samir did over many years, sort of in some sense in the wilderness. Not a lot of people paying a lot of attention, but it's incredibly beautiful, the stuff he's done to do that. And it seems to work extremely well. And as I say, Costas and Marika did a huge amount of work putting, and Kenneth Schneider putting this, making the precision holography of this story. Adding the momentum is a much, much more complicated thing. And so far, while superstrata are microstate geometries, and there are a hell of a lot of superstrata, there are, superstrata that involve arbitrary functions of 3 variables. So that's a lot of, give me a supergravity solution that depends on 3 arbitrary functions of 3 variables. That's a lot of phase space. But in terms of the string, in terms of the black hole, it's not by any means the size of the phase space of the black hole. It's getting close, but it's not there. The money is that you want the entropy of the system to grow as q to the 3 three halves, that's the area of the event horizon. If you put Q1 equals Q5 equals QP, the entropy is Q to the 3 halves. If you count the superstrata we've constructed so far, and you go to the right corner of the phase space volume, Masaki wrote a paper about last year showing that we've got to Q to the 5/4, I think. So it's a lot, but it's not quite there. And so reasonable people can differ, and hopefully Joseph will shout at me in a minute, but the point is supergravity may not capture everything. It may or it may not. There's always this question of how can I extend the supergravity phase space? But the bottom line is that smooth geometries also have stringy excitations about them. They have all sorts of perturbative excitations about them. And so even if the superstrata don't cover the whole phase space or with high density, it is certain that stringy excitations within them will contain a very much larger amount of entropy, and I think you can probably make a reasonable argument that stringy excitations of microstate geometries are going to be the way to think about black holes and black hole microstates. So the confessional thing is the match between D1 and D5 and the CFT structure and the states of the CFT is almost perfect. The D1, D5P superstrata are only a very limited subset so far of the states that we know have to be in the D1, D5P black hole. They are very specialized, very highly coherent states. And the question you ask is, can we do more? We have ideas about how to do more, and but so far this is the state of the art that we're talking about at the moment.
Great, thanks.
You're welcome.
Nick, another very basic question. So this parameter alpha that you wrote down on one of the slides, that like you had to choose this particular combination of.
Yes.
So how does it show up in like this parameter? Does it show up in the supergravity description?
It does, absolutely. So what? So let me see if I can pull up the sort of slide that we're talking about. Let me back it up. Somewhere here. Let me find it. Right, let me share the screen first, and then I'll scroll find it. Yeah, it does. And Joseph, I may want to get him to chime in a little bit on this, but let's see, share screen. Preview, that is. Okay, so sharing screen, there we go. So there was this, that's it. There we go. So the point is in here, yeah, so it's this parameter alpha. So what you should remember is how do you determine what this projector is? This is an algorithmic procedure, but it's a huge other subject, which I'll put references in the notes to. But basically what you should think of here is this is the mass, and then these are the charges. This would be the D1 charge. This would be the D5. This would be the D5 charge, because it's the coefficient D5 projector, and this would be the KKM. Sorry, this would be the angular momentum charge. And this is the KKM charge. So what this says is you have to lock those two charges together. They have to have a certain magnitude, which is constrained in terms of the D1 and D5 charges. So what it's telling you is that this solution will break supersymmetry if you just throw in any old amount of either of these two things. But if you tune these charges in exactly the right proportion to the D1 and D5 charges, you will wind up with a supersymmetric solution. And that emphatically turns up, because when you go into the supergravity, you will see that you have the option of adding angular momentum to the solution. You'll see that you can turn on Kurzweil monopole, and you put in arbitrary coefficients, and then you go, okay, let me solve the supergravity. You solve the equations, and part of solving the equations links some of these quantities together. And at the very end, you say, I want it smooth, and it basically locks all of these details. So this parameter alpha is a statement about a relationship between this charge, and this charge, in a very precise way. And you find exactly the same thing turning up in the supergravity when you just put in the particular sources and with arbitrary coefficients, and you find the equations of motion and ultimately smoothness tell you how they are all locked together to make exactly this. Or equations of motion, BPS equations, I should have said. So the answer is yeah, absolutely. And so we'll see this happen when I start actually solving equations of motion and actually writing down solutions. And you'll see it very clearly. As I say, the first non-trivial example I'll do is the D1, D5. But And you'll see exactly how the Q1, Q5, and the KKM charge gets related as required by smoothness.
Yeah, right. Thanks.
Sure. So as I said, I tried to get as far as I could today without actually writing down a single equation. Any other questions or comments? The next one will probably be on Thursday of next week because I have another commitment on Friday. So we'll probably move it to Thursday. And
some encounters in the morning, so there may be encounters.
Yeah, so probably Thursday afternoon. So in fact, Thursday afternoon works better for me, perhaps. So if we can tentatively say the next one will be 2 o'clock or so on Thursday of next week. Then I'm taking a vacation for a week, and then we'll pick it up again afterwards. So I don't know how long my energy will last, but I imagine at least 3 or 4 lectures.
Sounds good. Okay, so I'll stop the recording.
Okay.